Here we're going to look at question 12 from section 2 of the ENGAA specimen paper. So in this question we're told we have a mass of mass m, which is falling down with a velocity of v. It has a resistive force acting against it, F, due to friction or air resistance, which is equal to some constant k multiplied by the velocity v to the power of n. The question then tells us that when the velocity v is equal to v0, then the acceleration of our mass is just half the acceleration due to gravity, g/2. Then with this information, the question asks us to find the terminal velocity of our mass. So if you'd like to have a go at this question yourself, then please pause the video now, otherwise let's have a go together. So to try and solve this question, we're asked about the terminal velocity of our particle. So perhaps we should have a bit of a think about what the terminal velocity of our particle actually means. We've been told about a certain velocity v0, which has an acceleration of g/2. So what about the acceleration at this terminal velocity, which we're going to call vt? Well, at terminal velocity, it means it's the final velocity the particle is going to reach. So it's not going to get any faster, it's not going to get slower, it's just not going to accelerate at all. So at this point, the acceleration is going to be 0. So what we have here now are two different cases of two different velocities with two different accelerations. So how would we call these case 1 and case 2? If you want to think about these a bit more, then perhaps you should think about the accelerations, which might make something come to mind, especially since we've got forces up here. And that is going to be Newton's second law. So what about if we consider Newton's second law, or the resultant forces of our mass at these two different accelerations, at these two different velocities? So to do that, we're going to need to think about all of the forces acting on our mass. So what is it that's making our mass move downwards? Well, we've got a weight. And this is going to be the only other force acting on our mass. So with that in mind, we can go ahead and consider Newton's second law for both of these cases. To begin then, let's start with our first case 1, where v is equal to v0 and the acceleration of our mass is g/2. So the resultant force is just going to be the weight take away our frictional force at this velocity of v0, and this is going to be equal to the mass multiplied by the acceleration g/2. So this is just a simple case of using Newton's second law. This is the resultant force, and this is the mass multiplied by the acceleration. We can then go ahead and cancel this down a little bit. We can, since we have an mg on both sides, to give us that kv0 to the power of n is just equal to mg/2. Then we can do the same thing in our second case, where v is equal to vt of terminal velocity. And then here, since our acceleration is just 0, then our resultant force is just going to be equal to 0. So the weight is just equal to the frictional force. And now with this, is there anything which you can think of which we could do? So, one of these expressions has a terminal velocity in it, and then between them, they just have values which we know, or which we've been given in the question. So what we could do is we could merge these two equations together. And the easiest way to do that is probably just to cancel out our mg's. There's no point in leaving them in the equation, so we might as well just cancel them. And doing that is going to give us this, that kv0 to the power of n is just equal to kvt to the power of n divided by 2. Then, obviously, our k's are just going to cancel, and bringing the 2 up to this side and doing an nth root of both sides of the equation is going to give us that the terminal velocity is equal to 2 to the power of 1/n multiplied by v0. So this is just going to be our final answer, and it's going to correspond with answer B given in the question.